Good morning to all. We are from Annamacharya Institute of Technology and Sciences. Our project is on two-stage converter standalone PV battery based on VSG control. We the team members P. Deepika, Y. Jahnavi, D. Hajivalli, P. Lokeshwar. This project is under the guidance of P. Bhaskar Prasad. Two-stage converter standalone PV battery system based on VSG control. The contents of this project are objective, introduction, existing method, disadvantages, proposed method, proposed block diagram, simulation results, advantages, applications, software and hardware applications, literature survey, references. The main objective of this project is, in this project, a novel virtual synchronous generator controller is designed and implemented to adjust the inverter output. The VSG element and the maximum power point tracking MPPT are used to adjust the inverter output and to yield maximum power from PV scheme. The new control strategy design was evaluated and validated using MATLAB under different scenarios including load variations. The introduction of this project is PV systems are increasingly used as distributed generators worldwide because they are environmentally sustainable and clean. The price of PV panels has dropped significantly and they typically have DC power which is not always stable. As PV panels are linked to the grid, they require DC to DC for boost power and DC to AC conversions. However, as PV power is unstable, standalone PV units need an energy power storage component usually implemented by a battery bank. PV supplies change over time because of the source and conditions, variable nature under the load or grid specification demand. A single and a two-stage processes two methods used to integrate the solar energy with the load or grid. The first method is made up of inverters that convert DC to AC according to the load's demand. In the second one, however, the DC voltage supplied by PV cell is first increased and then inverted into AC as needed. Recent studies on two-stage grid converter of standalone applications have been limited. In a two-stage single-phase PV system designed to operate in a standalone configuration without batteries was presented. Research concluded that the device could adequately provide standalone power without the use of batteries. Thus, the system cost and maintenance can be reduced if the system is designed practically. Proportional integral controllers were designed to control a two-stage standalone system. The control goals were achieved with satisfaction and success as per the obtained results. However, these works didn't mention how VSG control operates under a two-stage converter. These were focused on a two-stage converter operating in a standalone mode with a battery based on the VSG control system application. This is the block diagram of existing method. When solar power is tracked from the panel, the DC to DC converter receives the power and this sends to inverter. DC to DC converter is used to increase the voltage or boost up the input voltage, and DC to AC inverter used to convert the DC voltage into AC voltage. Here we can see the LC filters like capacitor and inductor, the capacitor in parallel and inductor in series. These are used to reduce harmonics and for the better operation. This is given to the load. MPPT controller, which is known as maximum power point tracking. The maximum power is tracked from the solar panel and is given to PWM generator to produce pulses, and this was given to DC converter for triggering. Here inverter control input current and input voltage were given to the inverter controllers to generate pulses from the PWM generator and given to DC to AC inverter. It depicts the block diagram of two-stage standalone PV system. The first stage is composed of a boost DC to DC converter associated to its PWM generator and a conventional P&O MPPT. P&O, which is meant by perturb and observe. The boost converter has the task of stepping up the output voltage of the PV array, whereas perturb and observe maximum power point tracking aims to properly track the PV array's maximum power point. The second stage, which is in a single phase inverter controlled by two control loops, has been cascaded with the first stage. so that an AC voltage results. Inverter's output is connected to a second order low pass LC filter which consists of a parallel capacitor and a series inductor as shown in figure 1. LC filter has been chosen because of its advantages such as simplicity and ability of mitigating the output waveform's higher harmonic components. The disadvantages of this existing method are control capability is very slow and less, control efficiency is also very less. To overcome these disadvantages, the proposed method is given. In this proposed system, a two-stage converter with virtual synchronous generator control is considered. The VSG element and the maximum power point tracking are used to adjust the inverter output and to yield the maximum power from the PV scheme. The block diagram of proposed method is shown here. The maximum power from the PV array is tracked and given to boost converter, which is used to boost up or increases the DC voltage, and this sends to the inverter to convert DC voltage into AC voltage. Here RLC filters are used to remove harmonics and for the better operation, and this AC voltage is given to the load. Input voltage and input current are given to VSG controller to produce pulses, and it is given to pulse width modulation for triggering. MPPT algorithm where the input current and input voltage are given. This is used to generate pulses through gate pulse and it is used for triggering. Here the battery is used in this proposed method for the storage of excess power and excessive power. Here bidirectional converter is used because the excessive power from the load is returns to the battery and stores if we need excess power, we use the battery for the operation and it is again given to the inverter through bidirectional converter. PV array. This block diagram shows the PV array. Here the temperature is 25 because the maximum temperature range for photovoltaic solar panels is always 25 or 77 is indicated by the manufacturer's requirement. We may expect the highest performance from solar photovoltaic cells when they are able to absorb sunlight with the greatest efficiency. Here the irradiance means the production of light energy from the entire disk of the sun as measured at the earth is known as solar irradiance. Instead of viewing the sun as an image, we are doing so as we would a star. A measurement of the brightness of the entire sun at a particular light wavelength is called as solar spectral irradiance. The rating of solar panel is 40 volts. For open circuit voltage is 40 volts and short circuit voltage is 7.84. By multiplying both open circuit voltage and short circuit voltage, we will get the module power which is 313.7. The photovoltaic modules use light energy from the sun to generate electricity through the photovoltaic effect. Most modules use water-based crystalline silicon cells or thin film cells. DC to DC boost converter. We use DC to DC boost converter instead of step-up transformer because step-up transformer can indeed be used to increase the voltage of an AC power source. However, there are several reasons why a DC to DC boost converter might be preferred over a transformer for certain applications. Due to DC power source, a boost converter can take DC power source and increases the voltage to higher level, while a transformer can only work with AC power sources. Efficiency. Transformers can be very efficient at transferring currents between circuits, but they are not ideal for stepping up DC voltages. This is because DC does not produce a magnetic field, which means a DC voltage cannot induce a voltage in the secondary winding of a transformer. Boost converters, on the other hand, can be very efficient at stepping up DC voltages with efficiencies typically above 90%. The size and weight compared to step-up transformer, the size and weight of DC to DC boost converter is very light, and transformers can be bulky and heavy, especially when dealing with high voltages and high power applications. In contrast, DC to DC boost converters can be much smaller and lighter, making them ideal for using portable devices. The boost converter is one of the simplest types of switch mode converter. As the name suggests, it takes an input voltage and boosts or increases. All it All it consists of is an inductor, a semiconductor switch. There is yet another way of thinking about the operation of a boost converter, where L is the inductance of the coil and I is the maximum peak current. DC to AC inverter. Here we use the universal diode. DC to AC converters are one of the most important elements in power electronics. This is because there are a lot of real life applications that are based on these conversions. The electrical circuits that transform direct current DC input into alternating current AC output are known as DC to AC converters or inverters. VSG control. This is the block diagram of VSG control. Here input voltage and current are given to the power calculation. We can get active power and reactive power, reference active power and reference reactive power. By comparing reference and normal active power, we can get voltage and phase. This is given to sine wave generator to produce waveforms or pulses, and it is given to voltage control. This is given to PWM, pulse width modulation, to generate pulses. The VSG control system monitors the power output of the renewable energy source and adjusts it to match the power demand of the grid. It also monitors the frequency and voltage of grid and adjusts the power output of the virtual generator to maintain a stable power output. The VSG control system also provides fault protection, ensuring that the power output is cut off if there is a fault or disturbance in the grid. In VSG control diagram, we use 2E3 and 0.5E3, 2E3 and 0.5E3 because they are active and reactive power reference values which are mentioned in above table. The value of E is 10. 2 into 10 to the power of 3. This is battery. Battery can be defined as an electrochemical device consisting of one or more electrochemical cells which can be charged with the electric current and discharged whenever required. Batteries are widely employed in order to power small electric devices such as mobile phones, remotes and flashlights. Historically, the term battery has always been used in order to refer to the combination of two or more electrochemical cells. DC to DC bidirectional converter. This type of converter nowadays is mainly used in electric vehicles. It is also called a half-bridge DC to DC converter. When the buck and the boost converters are connected in anti-parallel across each other, with resulting circuit is primarily having the same structure as the basic boost and buck structure, but with the combined feature of bidirectional power flow is called bidirectional DC to DC converter. It works in both directions. Now the results of these project are, this is the simulation diagram of different irradiance on PV system. Power is tracked from the PV array and given to DC boost converter, and this is given to inverter to convert the DC power into AC power, and this power is given to load. These are the results for different irradiance on PV system. This is the PV voltage and this is also PV current. When compared to PV voltage, the PV current has thicker result because the variation of this current is very high when compared to voltage. This is the output voltage of boost converter. When this voltage increases or boost up, here the voltage increases up to 400 when compared to normal PV voltage. And the output current of boost converter also, the current boost up to the up to 9 when compared to PV current. These are the simulation results with different irradiance on PV system. Inverter output voltage. We can get the sinusoidal waveforms in inverter output voltage. And in output current it is also same, because it is thicker as the variation current is very high. And the main purpose of the the result of sinusoidal waveforms is due to this is AC, the voltage, the DC voltage is converted to AC as we get these sinusoidal waveforms. The load active and reactive power. Here we can see the reactive power is increases to the 2000 up to, and the active power, this is the active power which is less. This is a simulation results with constant irradiance on PV system. In above we can see the different irradiance, and here it is the constant irradiance. It is same as the different irradiance and there is no difference in constant and different irradiance, except after boosting up the voltage increases and the current is decreases. Here PV current boost converter current. After boost up, current is decreases and voltage increases. Here in above we can see that sinusoidal waveforms, due to as it DC is converted to AC, we can get these sinusoidal waveforms. This is the inverter output voltage and output current. Comparison table for different and constant irradiance. When compared to constant irradiance and different irradiance, the voltage, current, power are same in both irradiance except voltage with small difference. Comparison table without boost converter and with boost converter. In constant irradiance, there is lot of difference in voltage and current when boost converter is used. The voltage increases and the current decreases. In different irradiance, without boost converter and with boost converter, the voltage decreases, and without boost converter the voltage decreases, and with boost converter it increases. Vice versa, the current decreases with boost converter, and without boost converter the current is increases. Simulation of charging mode. This is the simulation diagram of charging mode. Here the battery is used to store the power through the bidirectional DC to DC converter. Here the charging mode increases in this state of charge. Load voltage also increases. Here we can show the reference and battery current. This is reference current and this is battery current. When we see simulation results of charging mode, the load voltage was varied in very large values to 200, and in load current it is varied in small values up to 5. This is the active power and this is the reactive power. In the charging mode, load voltage and current waveform, the value is at 0.5 because the step change in irradiance at 0.5 second resulted the change in voltage and current waveforms. This is the voltage and this is the current. We can see the current in very large variation, and this is the output voltage when it increases when compared to PV voltage, and the current also increases in boost converter. We will get more variations in current compared to voltage, therefore current waveform is thicker than voltage waveform. Simulation of discharging mode. Here we cannot use the PV panel for the power tracking, and we can use the power from the battery storage, battery pack for the conversion. Here the state of charge decreases in discharging mode and load voltage is constant. Reference and battery current are reference voltage this one and the battery current is this one. The simulation results of discharging mode, the load voltage is varied in very large values and load current is varied in very small values, and this is the active power and this is the reactive power. Comparison table for charge and discharge. In charging mode, the rate of charge increases and decreases in discharging mode. The voltage is constant in both charging and discharging mode. Current, power, voltage are both constant in charging mode and discharging mode. The advantage of this proposed method are quick and responsive control capability, high control efficiency, improves the frequency of dynamics. The applications of this method are renewable power system and electric vehicle. The software and hardware applications are in software configuration, operating system consists of Windows 7, 8, 10 and application software MATLAB and Simulink. Hardware configuration consists of RAM and processor, RAM with 8 GB and processor with 13 to 15. The conclusion of this project is the paper proposes two-stage converter PV systems including a battery unit, MPPT algorithm and VSG control used in the proposed control strategy. Additionally, a bidirectional converter control is presented. The combined control provided successful tracking under various irradiation scenarios thanks to the proposed method's quick and responsive control capability. In addition to the combined control performance test and the favorable effects on the whole system, it is seen from the bidirectional battery method that the control of battery modes also has superior control capacity. The MPPT control was subjected to efficiency analysis. The MPPT system has a 99% control efficiency. The experiment proved that the inertia increase greatly improves the frequency dynamics. This means that VSG can truly and very precisely model a synchronous generator. Therefore, it is considered a good control for this system. Literature survey of this project is P.S. Shenoy, K.A. Kim, B.B. Johnson and P.T. Crane proposes conventional energy conversion in photovoltaic systems are often forced to trade off conversion efficiency and power production. Next, X. Lu, K. Sun, J. M. Guerrero, J. C. Vasquez and L. Huang propose this paper presents the coordinate control of distributed energy storage systems in DC microgrids. Next, S. V. F. He, L. Yuan, Z. Zhao, T. Lu and J. Ma proposes solar photovoltaics categorized under distributed generation to meet the demand of power per load variations and also helps in assisting the existing power system. Next, M. Shreyas Tegan proposed this paper gives an overview of previous studies on photovoltaics devices, grid connected PV inverters and control systems. The references of this project are Y. Yang, F. Blabbering and M.G. Simos power control flexibilities for grid connected multifunctional photovoltaics renew, and these are the references of this project. Thank you.